Okay, welcome to the 25th video in the Discrete structure series, and this video is going to be the start of a new topic, Rules of Inferences. And to be more specific, we'll be looking into the idea of arguments, premises, and the validity of arguments. And then we'll look into what an argument means in propositional logic, and following that, we'll be looking into the 8 laws of inferences in propositional logic. Okay, let us begin with a discussion about arguments. An argument is a sequence of statements followed by a conclusion. So let us demonstrate by writing a statement and a conclusion. Let's say it is cloudy and it is the rainy season. Why not? And these two are the sequence of statements mentioned here. And then let me write a conclusion. It will rain. So this statement has a set of premises and it has a conclusion. Therefore, this is an argument. And based on this example, we can also have a look at our other terms. Premises are the preconditions that must be true for the conclusion to follow. So for example, this example is asserting that 1 and 2 are true, therefore the conclusion is also true. Therefore, the sequence of statements mentioned before the conclusion are called premises or preconditions. And the process of getting to the conclusion from the given premises is the process of inference. So an inference can be defined as a process of reaching a conclusion based on evidence or reasoning. And then we can talk about the validity of an argument. We can say that this entire statement is valid if from the given premises the conclusion can successfully be inferred. We will look at more concrete examples, but even in this context, if ensuring these premises does cause it to rain, we say that this argument is valid. However, the criteria for an invalid argument is slightly different. An argument will only be invalid if all the premises are true but the conclusion is still false. It is exactly similar to the discussion about implications we had earlier. If the premises are false in the first place, the argument is automatically validated. Let me show you with an example. If I were rich, I would purchase a car. So this is a valid argument. I am not rich, neither do I have a car. But I can conclude that this argument by itself is valid because I am only claiming if I were rich, I would do this. And the only situation where this argument would be invalidated is if I were rich but still didn't purchase a car. Therefore, the validity of an argument does not directly depend on the validity of the premises. All that a valid argument requires is that if these premises are true, the conclusion also must be true. So with that idea in mind, let's look at another example. Okay, so let us put some context into this example. 1 and 2 are my premises and this is my conclusion. And since this example is not as vague as the rain example, we should be able to make sense of this easily. So if you have password, you can log in. And the second statement says that you have password. Therefore, we can conclude or infer that you can log in. And this is my conclusion. And here maybe I could logically tell that whatever process of inference was used is correct. Because if you have password, you can log in and you have password, right? Therefore, you can log in. So that is straightforward. However, we need to formalize this. What is the exact rule that is allowing me to make this inference based on these premises? So if you look in this case, this statement looks like P implies Q. If you have password, you can log in. And the second statement says that you have password. That means P is true. Therefore, some law must exist that will tell me that if P implies Q is true and P is true, I can conclude that Q is true. Because that is what I'm doing here. You can log in is my Q. And in fact, these laws do exist. This one is called the law of detachment or modus ponens. So next we'll go through the 8 laws of inference on propositional logic, including modus ponens. But my idea behind the demonstration of this example was to show you the thought process behind recognizing these sentences and deriving these conclusions. That said, we'll move on to our next segment where we'll discuss these laws of inferences for propositional logic in a bit of detail. The first law that we're going to look at is called the law of detachment or modus ponens. So the origin of the word modus ponens relates to this phrase mode that affirms. And mode that affirms means that it enables a proposition to be true. Let me demonstrate with an example. So let's say we have P implies Q. We just saw it in our earlier segment. And if I have P, I can derive Q. So I think this will not take much explanation. The implication suggests that every time P is true, Q is bound to happen. And the second statement suggests that P has been true and therefore we can conclude that Q is bound to happen. And the proper and more compact way to represent the law of detachment is as follows. We say that if P implies Q and P, if both of these things are true, I can use this to imply Q. And this should not be confusing at all. All we are doing here is to take all of our premises in conjunction. So we take all of our premises, we do the conjunction of them, And then we mention that the conjunction implies the conclusion. And this is the same as saying if all of these premises are true, then the conclusion is also true. The second law that we're going to look at is called modus tollens. And we should think of this as the mode that denies. And if you are curious, there is no name like law of detachment for this one. I did a little bit of research and couldn't find a name. So we'll just call this modus tollens. But the idea behind this law is that it denies the premise given that the conclusion didn't happen. And that comes from the law of the contrapositive. So if P implies Q, I'm able to say not Q implies not P. If studying in the exam implies that you pass, you didn't pass means you didn't study. We have discussed this in detail in our video about implications. I'll add one more detail. If you cheat, you pass also. So if you study, you pass. If you cheat, you pass. Okay, so I have two implications here. Study implies pass and cheating implies pass. But if I know that you didn't pass, if I know that not P is true, I can conclude that both not S and not C both are true. Because you didn't pass means you didn't study and you didn't cheat. And none of the 20 reasons that could cause you to pass happened. Therefore, from this given implication P implies Q, I'm always able to write not Q implies not P. And essentially, if I know not Q is true, I can also say not P is true. So let me write this down. Let's say I have P implies Q and then I know not Q. Okay, I can use this to infer not P. And you can see how this law helps me deny the premise. And if I want to write this in a formal way, like this one, I can simply write P implies Q and not Q implies P. Okay, next we'll look at the hypothetical syllogism. So let me write two propositions and a conclusion here to show you what I mean. Okay, so I've written this example here. If I were rich, I'd have a car. If I had a car, I'd go to a vacation. If I were rich, I'd go to a vacation. Can I conclude this based on these two premises? And I think you'd be able to see that this entire argument is a valid argument. And so we can now try to formalize this. The first statement looks like P implies Q. And the second statement looks like Q implies R, something else. Q implies R. And from this, I'm able to conclude P implies R. And it should be easy to see here. P implies Q and then Q is implying R. That means P will imply R. This is just a cause and effect. And this is also called the transitive rule. But I hope you see the main point here. The reason we are calling this a hypothetical syllogism. By the way, syllogism refers to the reasoning process. So this rule is essentially saying a hypothetical reasoning process. None of my premises are true. Okay. I am not rich. I don't have a car. And I have never been to a vacation. And despite all of that being hypothetical, it is still a valid way to infer things. For example, if the size of the sun were to grow by 2 times, this is what would happen to the earth. I mean, that is something that I would want to know. So in science and even in practical life, we are often interested in what would happen in certain hypothetical situations. And this particular syllogism helps us in that process. And can we try to write this formally? P implies Q and Q implies R. And I can use this whole thing to imply P implies R. Okay, it's just the same pattern. This and this implies whatever the conclusion is. Okay, next we'll look at the disjunctive syllogism. And we know what a syllogism means. A disjunctive syllogism is just how to reason on a disjunction. So let's say if I have a disjunction P or Q, and let's say I have another premise not P, then I can conclude Q. Because this disjunction suggests that P or Q must be true. And since P is false, Q must be true. And so we can write P or Q and not P. I can use this to infer Q. Okay, that was quite straightforward. Moving on to addition. So this one should also come really intuitively. If I have P, I can say P or Q. Because P by itself is true, right? And in an OR statement, only one thing needs to be true. Therefore, if I know that something is already true, I can keep ORing anything with it and the result would always stay true. And so this law is called the law of addition. P implies P or Q, okay? Let's have a look at simplification. So simplification means simplifying from a conjunction. So let's say if I have P and Q, this means that both P and Q are individually true. So I can conclude P, I can also conclude Q. So we can just express this as P and Q implies, whatever you want, P or Q. You could choose either one. So next we'll be looking at the law of conjunction. And this has a pretty simple statement. If I have a set of propositions that are individually true, I can conclude that their conjunction is also true. So in this particular example, since P is true and Q is also true, I can say that the conjunction P and Q is also true. And obviously this would apply for any number of propositions. And in fact, this rule is so basic that if I try to formalize this, I just get an identity. So if we try to write the equation same thing as we did before, I get a P and Q. And this would imply a P and Q. So this is quite obvious to see, but a useful rule of inference nonetheless. Okay, so next we're going to move to the last but arguably the most important rule of inference, and that is resolution. So this one has two premises. The first one is P or Q. One of P or Q is true. And the another one is not P or R. Okay, if P is false, R is true. Then I can use this to infer that one of Q or R must be true. And we say that resolution is one of the most powerful proof methods because it helps us to derive new facts. And this should be said lightly because all the rules of inferences in fact help us derive new facts. But this one specifically creates new relationships because in my original propositions, I only have relationships between P and Q and P and R. There is no direct relationship between Q and R. But I can use the process of resolution to use P as a dependency thread, and then I get a dependency between Q and R. And let us quickly see why this is true. P has two possibilities of being either true or false. Okay, let's look at both cases. Whenever P is true, I can conclude that not P is false. Therefore, for this disjunction to be true, R must be true. And on the other hand, if P is false, then the first disjunction requires Q to be true. So no matter what value for P I choose, either Q or R is bound to happen. But since I do not have the truth value of P in advance, the best I can conclude is one of Q or R must be true. Okay, that finishes the discussion of the 8 most important rules of inferences in propositional logic. We'll stop here, and in the next video, we'll be looking at the idea of fallacies, instantiation, generalization, and we'll see how we can extend the laws of inferences to quantified statements. So I'll see you in the next video. Until then, have a good day and bye.